that there is one of these wildfires that turned into a big wildfire. I just happened to be up there the day it started. So our Sierra Nevada is overstocked with trees. These dense canopy forests are a product of our resource extraction economy, and are vulnerable to high severity wildfire and drought because there's so much fuel out there because of the wildfire suppression and the unsustainable logging. And there's just zillions of small trees out there, and they're all too common in our forests. Versus a historical forest, this is an area in an experimental forest where thinning has been done to take the forest plots in the forest back to, say, around 1900, a century ago or more than a century ago, conditions when it was a more open forest. You see quarter-acre clearings, you see patchy vegetation versus the control, which is the way it was before the thinning. This is an on-the-ground shot of the same forest, where the forest used to be, like in the foreground, small number of large trees, mature canopy, versus the background, which is one of the control plots, lots of small trees, which you can, in some places, can hardly walk through. So I'm going to touch on 5 things briefly today. Drought. This is a photo, happens to be at one of our field study areas, is right near here, where we had basically 100% conifer mortality during the drought that ended in 4-year drought that ended in 2015, the water year 2015. The reason the trees suffered mortality is because they basically ran out of water. We've known for decades that the Sierra Nevada developed these rich forest canopies because the root zone goes down several meters. Root accessible water goes down several meters in this, contrary to what some modelers put 1 meter of soil, because that's what it is in some more humid areas. So we were measuring the drawdown, and this is our estimate of the plant accessible water based on our measurements of soil moisture. And each year it depleted until it couldn't deplete anymore because it had reached the bottom of the root zone. That is, the precipitation was less than the evaporative demand of the forest for several years running. And part of our critical zone observatory, the Southern Sierra Critical Zone Observatory, included a transect of measurement sites going from the oak savanna up through the high Sierra, the pine oak. The pine oak forest was next, the mixed conifer forest, and then the more of a red fir lodgepole forest. At each site, we had an eddy covariance flux tower. I'm only showing 3, but there were actually 4 there, as well as extensive soil moisture, precipitation, and other measurements, so we knew the water balance plus other attributes of the critical zone. I'm really going to talk mostly about water stuff today. And yeah, we have tall trees there, so this tower was, what, 55 meters tall. Yeah. We've since, this one remains. We took out some of the other towers, but Neon has put in 3 towers, which basically cover the 3 that we took out. And we've moved our eddy covariance measurements further north in California now. This is in the Southern Sierra. So basically with these eddy covariance towers, we established, I think for the first time, accurate evapotranspiration measurements across the Sierra Nevada. This is a Landsat image of the Kings River Basin. Fresno is down here on the left, the Sierra Nevada, and basically on an annual basis, each dot is 1 year of evapotranspiration measurement at the flux tower correlated with satellite-derived NDVI, basically greenness. So greener, more evapotranspiration. And you can see here, the high Sierra is low because the growing season is short. The lower elevations, the oak savanna, is lower because it's precipitation limited. And the happy zone for trees is right here in the middle, the very dense mixed conifer zone, where it's not too dry and not too cold, year-round growing season and plenty of water. And so the runoff comes from this higher elevation or mid elevation, and especially the high elevation. So you'll see me using a basic water balance here, typically annual water balance. And at our measurement sites, we actually could track change in storage because we had multiple measurements of change in storage. So I won't dwell on that. I think everybody's probably seen a water balance before. Yeah. Now, another result from this is that we can actually predict the drought stress. We could have predicted the drought stress, but we didn't think about it in time. And by the time we thought about it, the trees were already dead. So basically, the cumulative water deficit that I showed on that earlier XY graph, we can track by our eddy covariance measurements using that relationship between ET, evapotranspiration, and NDVI. We've scaled our evapotranspiration product basically now across all of California and are getting ready to scale it further across the Western US. It's an annual time step. But anyway, the cumulative multi-year water deficit is shown here. Instead of XY, it's latitude versus elevation. So we can see the elevation pattern here, but elevation, it would look similar. It would just be compressed if I did an XY graph. And this is an index of tree mortality from, I believe from Landsat, in this case, NDMI, Delta NDMI over that period. And then this is based on aerial surveys that the U.S. Forest Service did of dead trees. And in our paper, we showed that these all three correlate fairly well, pretty well, which gives us then a predictive ability of using P-ET to predict tree mortality. And we've provided that, but the trees seem to be dying faster than our predictions anyway. And so this drought-induced mortality is very serious. These are data for 78 giant sequoia groves. We've lost, due to either fire or drought, we've lost about 30% of our giant sequoia trees in the Sierra Nevada, these iconic giant trees. So this is just a graph from 1985. This paper picked up through 2015. Precipitation, we use PRISM data for precipitation, temperature, and evapotranspiration from our product. I've shaded 2 drought periods. You can see that toward the end of both droughts, this was longer drought but less severe. It wasn't as hot. This is an unprecedented hot drought where you can see the temperature was much higher and the evapotranspiration dropped off. The trees are using more water, but they use the water up, as you saw from the earlier graphs. So we asked the question, well, what if the drought was longer? Because in the millennial scale record, we see droughts that go, 6 years, 8 years, 12 years. And so we said, well, let's impose the same temperature and precipitation conditions. And yeah, okay, we're looking at a huge reduction in evapotranspiration, reflecting a widespread mortality. Maybe wipe out most of the giant sequoias and the mixed conifer forests that are around them. And this is based on more a statistical approach and LSTM model. Yeah. So drought is one threat to the survival of the Sierra Nevada. Wildfire is another. This is a creek fire, which was near the same area as our main research study sites, but much larger. This is the southern Sierra Nevada. Again, Fresno is a little bit off to the left here. Warming temperatures. So let's look at conditions over this Landsat period, 1985 to present, when we have good evapotranspiration data. So this is the Creek Fire polygon. Blue is high evapotranspiration, 2012. There was a particularly wet period that ended in 2012, water year 2012. Then the drought came. We see some lower evapotranspiration due to the drought. And then 2021, huge drop in evapotranspiration due to wildfire. So these effects are real, they're quantifiable. And of course, you know, as you can see from the earlier drought, you have a wet period following a drought, the trees grow back, they're happy, and put on more biomass. So the evapotranspiration will recover fairly quickly during a drought. The carbon stock takes much longer to recover. So restoration, what are we doing now to try to mitigate this problem? Because it's all about restoration. The U.S. Forest Service and state of California have pledged to thin, like this, either with mechanically or with controlled fire, about 1 million acres per year. And we're doing less than 10% of that now. So projected flame length, this is an index of fire severity. Yeah, this is just ground fuel only, a 6 foot, 5 foot, 6 foot projected flame length. There's a hole in the middle here because we cut out the agricultural valley. We're looking at just the wildlands. Yeah. So this is the Sierra Nevada is our main water supply. It has a threat of, when you have a 6 or 8 foot flame length, you're going to get the fire from the ground up into the canopy probably because you have ladder fuels. So we want a lower flame lengths for the ground fuel. So how are we doing this? These headwater forests, I like to say, are multi-benefit assets, our natural capital, and we need a multi-benefit approach. We're no longer managing these forests just for timber production or cattle grazing. We're looking at the many multiple benefits that we get from forests. And we need systems thinking to do that. That is, think about the whole picture, the biodiversity, the recreation, and so forth. This is an area that was thinned, but not thinned enough. And this is an area that wasn't thinned. So I just like to throw out that sustainability is a powerful metaphor for thinking about a multi-benefit management, whether it be on these forests or anywhere. We think of sustainability in these ecosystems as being the ecological integrity, that is resilience to perturbations like drought, wildfire, and so forth. We think of the human well-being, which we call ecosystem services, and that's been a major focus of what we're doing the last few years, is valuing ecosystem services. And equity or environmental justice. These rural areas provide low-cost housing to people across California and across the Western US. We're looking out for future generations also. So we need clear objectives. And yeah, this is another big wildfire in the background. I happened to be out one day as the fire was getting going. There's 3 big plumes here. Became the Dixie Fire up in Northern California, Northern Sierra. Our system's objective is to increase the pace and scale of transitioning from this destructive wildfire regime to a beneficial regenerative wildfire regime. We want more area burned per year, but burned at a lower severity. Just ground fires that keep the fuel loads down, that keep the understory down, and the dead fuel down. And so it's not just a one-time investment to go in and do this forest. Right now it's mechanical thinning. If you put controlled burn in there, the vegetation is just too dense, and it could easily get up into the canopy. And there have been several places where that's happened in the Western US. So we want these, if it's a low severity fire, the national parks are just letting it burn, which is what we want to do going forward. Here's an example. There was a Star Fire in 2001. This is 20 years later. It's full of these dense shrubs, and eventually the conifers will come back and take over. But again, that's why the ET comes back right away. The evapotranspiration comes back right away after disturbance. It takes much longer to build up the biomass, the carbon stocks. So we're going through, I say we're part of applications partnerships, going through and thinning and masticating. This is right across the road from each other. Also doing meadow restoration, getting trees out of meadows where there used to be meadows. So many, we have only a fraction of our meadows remaining intact with the high biodiversity in the Sierra Nevada. So ecosystem services, briefly touch on what we're doing. Forest restoration provides many benefits in addition to reducing the probability of high severity wildfires and the smoke damage. This photo was taken at one of our research sites. The fire is still a couple miles away, but shortly after this, the electricity went out when it burned through the power lines. This is now a neon site. So thinned forest, here's a thinned forest without the large mature trees, because this was private land and they pulled the big trees out before selling it to the a nonprofit conservancy. But we thinned it anyway, and you can see there was mastication done, which leaves fuel on the ground so that we could still get reasonable flame lengths here, but the trees are far enough apart, we're not going to get a crown fire. It'll go through here as a ground fire. So removing small trees makes more water available, cycling back to the hydrology now. If you have fewer trees in the forest is using less water, as you saw from both the drought and the wildfire examples. So we have better in-stream flows and more water for downstream food production and urban areas. And yes, we have a water deficit in our agricultural areas. We're looking at having to fallow, I don't know, maybe up to 1 million acres. There's only about 8 million acres irrigated, and we may have to fallow 1 million acres of that if we're going to stop over pumping our groundwater. So we're looking for water supplies any place we can to continue that very productive, profitable agricultural industry. Hydropower benefits are also important. That many of these rivers have high elevation hydropower on them. And yeah, when you get a high severity wildfire, you get erosion and sediment flow. So we're not making good use of our forest products yet, which is a problem with the ecosystem services. these are non-merchantable timber. Nobody wants to buy these trees that are this large, so you can haul them out to a biomass plant, but you have to pay a huge amount to get them out of the forest. So we're trying to develop a biomass economy in California rather than just leaving these in place to burn or decay. And air quality and health issues have become a huge issue in California due to the continuing wildfires. So reducing the wildfire severity through forest treatments is key. And the water benefits are central to getting that done. This is the Sierra Nevada again. So Lake Tahoe would be here, Fresno would be here, Merced down here. So looking at a project, this is a typical thinning project that we're involved in. It's about 5,000 hectares. You see these polygons that were thinned. The cost of that thinning ended up being a little under $5,000 per hectare, but the net present value of just 6 of the benefits, hydropower, water sales, projected to be about $4,000 per hectare. And the fire-related benefits, keeping the timber stock in place, not saying we're going to harvest it, but we get better carbon storage, erosion regulation, air quality. So mapping these benefits is what we're doing, and we've extended that across the state. Yeah. So we've got to show the value proposition, especially to the water agencies. We are having some success getting water agencies to help pay the cost. Because if these, let's say these are costing, I'll jump back to acres. Let's say they're costing $2,000 per acre to do these forest treatments. And if we want to do 2 million, if we want to do 1 million acres a year, that's real money. That's what, $2 billion. And this doesn't include the administrative cost and so forth. So we're up to about $3 billion a year is the need here. The state is putting somewhere around $500 million into it. The US Congress is putting much less than that into it. So we're looking at a financing environment where the beneficiaries pay for this. And a couple of water agencies in the Sierra Nevada have stepped up, and we have conversations with some of the urban agencies. They're reluctant at first because they have been getting all these benefits for free for the last many decades. Why should they start paying for them? Their boards of directors and elected officials say, well, that's just another tax. Why should we pay it? Let somebody else pay it. So we're looking for a sea change we're looking for changing the scope of water management agencies to managing their green infrastructure, not just their built infrastructure. And it's about partnerships. So we get this is some of the project partners. We get together once a year and assess how things are going on the ground. This is an area that was just thinned. Since then, there was a controlled burn went through here to burn the biomass. And the Forest Service can't do it. They simply don't have the capacity to do it, even though it's their land. So we formed these partnerships of local interests, and the university, yes, we're part of the partnership because these partners value research. They're all across the political spectrum, from right-wing Republicans to liberal Democrats. And so we come together over managing these landscapes. So yeah, monitoring research are part of the adaptive management cycle. There's my colleague, Safiq Khan, UC Merced colleague, who's taken over most of the field work as I focus more on synthesis stuff these days. And our third partner, Martha Conklin, just retired last year, so she's not getting out in the field to do this stuff anymore. Yeah. I like to say we can't just model our way into these solutions. We need data. We've got to have field-based, real data to do this. If you think you can solve the problem by sitting in your office and changing the parameters in the model, you're mistaken. There's just too many uncertainties here. We've got to have data. And let me just do one quick, we're getting the word out to the public. We have a film that was out on PBS a couple years ago. We got a new one coming out this spring.
The watershed as a security issue, but when you back up the bus and you look at what are the foundational principles that our safety and security are relying upon,
that's Janet Napolitano, former UC president.
Food security and, you know, ensuring that those things.
Former Homeland Security Secretary.
Taken into account and planned for.
For so many people in California, they don't know where their water comes from. Every developed region of California depends.
He was managing the largest irrigation district in California.
Distant regions of the state, the watershed.
California is a canary.
He's the secretary of the Resources Agency.
We're already experiencing more severe wildfires, droughts, flooding, coastal erosion, sea level rise, and extreme heat.
We say, well, what's the new normal? Well, there really is a new normal. The new normal is warming.
Our forests are currently overstocked.
He's a water manager.
Too much vegetation.
They're helping to pay for forest restoration.
It's just. We've all said this could be.
He's from the ag sector.
It's called wildfire for a reason. If you don't decide to control a fire.
Cal Fire.
Say 20,000 acres and then the wildfire controller.
When we were getting ready to leave, my son, my 9-year-old, was asking. Was asking me, Mom, what's the likelihood that our house is gonna burn down?
She's with an NGO.
California has changed so much as we came and we kind of conquered.
Oh, there's my colleague and spouse, Martha
What we've
Conklin.
managed to wreck in a short couple of 100 years should be a lesson for all of us to look at.
When we talk
He
about
has a-
trying to address the problem.
She's a UC
in terms
Merced
of forest
professor.
health, in terms of fire, and in terms of holistically, you know, restoring a sustainable forest system. We already know what works. We just have to go out and implement it.
Okay, so if you look at online, you'll see the Wild and Scenic Film Festival, which we're screening the film there. We screened it across the state, and hopefully we'll push it out on PBS next month. So take home points from what I've said. Actual evapotranspiration is a primary response variable for measuring our forests. We can measure it on any arbitrary polygon using the scaling tools that we've developed based on eddy covariance data and satellite data. Cumulative P minus ET is a direct and primary response variable. It's a forward-looking index for drought. We can use it as in a predictive method. In a warming climate, we've got to have lower vegetation densities. And to do that, we're going to have more active management, putting a lot more money into our managing our green infrastructure with benefits that far, far exceed the costs. The water-related benefits are large and result from these fuels treatments. Wildfires can also give you water benefits, but they really screw up some of the other benefits like habitat and recreation and so forth, carbon storage especially. So we take the systems view. We've got to do, we don't want just the water benefits, we want all the benefits. So managing the Sierra for multiple benefits is expensive, and we're continuing to develop the tools to inform the planning, prioritization, monitoring, assessment of this. So let me stop there.
Thank you, Roger. That was very interesting. If anyone has question for Dr. Bales, please speak up. I can start off. I can see Aaron had a question in the chat, which was how connected is the groundwater from the Sierras and the basin west?
Yeah, you get recharge of the valley groundwater basins through some subsurface flow, but it tends to be more in these relic alluvial channels, I think. It's not my area, but you do have some preferential recharge in some of these narrower channels coming down. Across the whole mountain front, I think there's areas without much subsurface recharge of the valley groundwater. The groundwater is not very deep. I mean, yeah, in the Sierra Nevada, because it's granite, basically, granite diorite.
I had a question. So kind of what you're explaining is that you're trying to get things back to how they were pre-human settlement with managing the forest, thinning, and not allowing fires to go into the canopy as often, is my understanding. I might be wrong on that. But do the management practices you're suggesting and propose, do those eventually get back to that point where natural fires could burn and kind of do some of the management for us without having a lot of the drawbacks of the large fires we see today?
Yeah, well, there's 3 points there. Going back to pre-1900 conditions is a good goal, but not a sufficient goal given the warming climate. We're going to have even less fuel and fewer trees than we did in the wetter but cooler periods historically. Second, these fires weren't natural. They were set by Native Americans. And this, so part of the resource extraction was killing the Native Americans because we had to get rid of them in order for Western interests to take over the land. So, and that's when the controlled burning stopped. Native Americans used to set fires to keep the forest more open. Yeah, so lightning fires are important, but they weren't sufficient to. They're not sufficient to control the wildfire, and we can't. We can't really completely go back to these pre-development conditions because the wildland-urban interface is everywhere. You and I like going to nice hotels in Yosemite and Lake Tahoe and so forth. There's low-cost housing scattered throughout the Sierra Nevada. There's expensive vacation homes scattered throughout the Sierra Nevada. Some of those are going to burn, and the insurance companies will stop reimbursing people for it. They pulled out of a few rural communities, but these rural communities are important for local jobs and for many things in the state. So I think we're going to have to start setting some priorities for who we insure out there in these areas. It's somewhat of a wicked problem to deal with here. I don't know, ask again if I missed a main point that you were asking.
So I think one of the points you're trying to make is that the reason that you're looking to thin and have lower vegetation densities is that each one of these trees pulls out and contributes to the evapotranspiration of the water from the ground. And so that exacerbates the whole system. And if there hadn't been the thick, dense forest, it might have, if you cut the vegetation density in half, it might have been able to survive that last bit of drought. That's the main point. So it's not that we're trying to like thin the trees to reduce these fires. That's a secondary thing. We are also doing that, but we're also just trying to, by the numbers, each one of those huge trees sucks water out of the ground.
That's a great view of a water resources manager, but the public has actually the flip
right
view. They want the forest thin to control the wildfire severity, and the water is a benefit. Yeah, I mean, forest managers lose their jobs when they let a fire get out of control, and towns burn when a fire gets out of control. So those are the those are the billion-dollar losses. Water agencies need, as I say, water agencies need to expand the scope of their responsibility. Yeah.
Any other
Water rights
questions?
holders-
Oh, sorry.
Water rights holders are also property rights holders in the Sierra Nevada. It's not just owning the land. They own the water rights, which is in many cases more valuable. So I keep saying they should be putting some skin in the game. They can pass those costs on as these two agencies that are paying for thinning that we're involved with are doing. Sorry, I just thought of that.
No, that's okay. There's a couple of questions in the chat, actually.
Oh, okay. I don't
There is a
see them.
question.
Yeah.
That's okay. There is a question from Lee McDonald, which is how much do the water yield benefits vary between drought years when they are most valuable and the wetter years when they may not be as valuable?
Yeah, well, there's a threshold you need to get to in order to see the dry year benefits. In terms of revenue, you can sell the marginal cost of that water, extra water during a dry year is about $1,000 an acre foot. During a wet year, you give it away. Super wet year like we had last year. Nobody wants to buy it but we're trying to change that by implementing more effective managed aquifer recharge for floodwaters in California. So again, it's a systems view, taking a whole watershed perspective. If we have this extra water during wet years, can we make it valuable by temporarily short-term flooding almond or grape areas planted in almonds, grapes, and so forth, where the infiltration capacity is high enough to get the water into the ground. So to push the value up to maybe a couple $100 an acre foot, at least during these wet years.
Roger, Lee McDonald, I don't know if you can hear me.
We can still get some runoff during the dry years if we take the fuels down to a certain threshold. Yeah. So that's where our data come in, is to maybe more precisely make those estimates.
Any idea of the order of magnitude of that threshold for the mixed conifer?
Please, everyone, mute yourself if you're not actively talking, please. Thank you.
Yeah, is there another question in the chat that we should go to? Yeah.
Yes, there is one that just got posted from Erica Dorr, which is when working with the public, including stakeholders, what are some of the most effective ways that you have engaged people of all sides of the issues to grasp the all systems thinking that is so critical to this work?
Yeah, in one of the projects, you need a champion that is effective in bringing people together. And in one of the projects, we worked with the Nature Conservancy, and they did that because they have a very strong local presence in California. They started talking to the various county supervisors, the water agency board members, other NGOs, tribes, and so forth. And pretty soon and us. And so we started taking these field trips together to look at the forest and talk about what needed to be done. And the Forest Service was part of that. And then it just came together. When you get these partners together, they'll figure out how to do the financing. In another case, I work with a nonprofit called Blue Forest Conservation. You can look them up on the internet. They advance the financing. They have investors that will advance the financing for forest restoration. And then the beneficiaries can pay back over time, over the life of the benefit. And so that, using a forest resilience bond, they were an effective convener to help bring people together on another project up in a little further north in the Sierra Nevada. And so you need that catalyst there, and who has the credibility to bring people together. And you want the university to be part of it, if possible, because we're filling some very big knowledge gaps around these projects.
And so if I can follow up on that question, would you consider that the knowledge gap is the biggest challenge to get more people working together on this problem?
No, it's not, but in our surveys that we've done, and you can look at some of our other papers where we've looked at what are the impediments there. Actually, that maybe that one's not submitted yet. There's two capacity gaps that are huge. And one is we just don't have enough trained foresters and other professionals to do this 1 million acres per year. And second, we don't have enough capacity for using more material coming off the forest because mills have shut down. You know, one of the people in that trailer of the film has put together a small company where he hires Native American young people, and they do a lot of the handwork that needs to be done in the forest. Well, we need 100 more of those types. So there's capacity limitations all throughout the labor force. Our community colleges are trying to address that. And then third would be, you know, getting the partnerships together so that we can do this. Partnerships are a real key. So I keep telling that to my colleagues at the state, saying you've got to provide some financing to get these partnerships together. And they say, well, you know, this is what the legislature told us to do and blah, blah, blah. We just manage the money that goes to thinning. They're starting to get, no, they're starting to get it, yeah. So the knowledge gaps are probably fourth after that.
Okay. Interesting. Well, thank you. Anyone else have another question for Professor Dr. Bales?
Yeah. Well, I hope this puts a different perspective on. I'm sorry I only had a couple of graphs in here, but you can have some hydrology talks with lots of graphs.
That's okay. I think I skipped one question in the chat because the bubbles were following each other. So it's actually another question from Lee McDonald, which is, I guess, a follow-up of the first one, which is how much year to year carryover is there in general in available water, or what proportion can the trees and other vegetation extract if the total soil reservoir is full?
Yeah, okay, so the trees, the average in these mixed conifer forests, they're going to need 600 millimeters per year, plus or minus a couple hundred millimeters every year. Evaporative demand of the forest is basically the same every year. And so we have a Mediterranean climate, so we have a dry season. So already about a third or half of that comes from subsurface storage during the dry season. That is then replenished during the wet season. If it's not replenished because there's less precipitation than the water that was extracted, then it goes down. And you have that several years over, it just keeps going down, down, down. So we can get at least a meter, in many of these areas, a meter of water. Well, let's say at least half a meter, in many cases, a meter of water to serve carryover needs during dry years. And in some areas that'll go 3 years, in some areas that'll go 6 years, depending on the temperature and the density of the vegetation. So I think we're looking at, with the thinning, being able to maybe survive some of these 6-year, maybe even 8-year droughts in the Southern Sierra, where we have the giant sequoias. But that's a hypothesis, not a proven number yet. We're still working on, as we have time, still working on things like that.
Yeah.
You're asking about the east side of the Sierras? No, it's qualitatively similar, but the forests are already much less dense because we have the rain shadow effect, so the precipitation drops off by about half on the east side, and they haven't had the you know, the unsustainable logging, and it's still more of an open forest. So the one area that is really critically overstocked is Mammoth Lakes. I don't know if anybody's ever been to the Mammoth Lakes area, but that's sort of a second Tahoe in terms of recreation, and it's the largest ski area in California. It's a huge summer resort area. It's where the people from LA go. They drive up the east side of the Sierra Nevada to Mammoth Lakes. So they have what they call a donut project. They're trying to thin the forest around Mammoth Lakes. Yeah, so the Bay Area, Northern California people go to Tahoe, Southern California people go to Mammoth. Yeah. Different tree species. Yeah, it is on the west side. You have the in the mixed conifer zone, you have the white fir, ponderosa, and Jeffrey pine, sugar pine. You see more, I guess, lodgepole and ponderosa in parts of the eastern Sierra. I'm not a forester, so I'm giving you my at least I can identify them when I'm out in the field, but I can't always remember what the main species are. But I think that's a good enough answer.
So the east side didn't suffer as much as the west side for the drought.
Exactly right, because the forests weren't as dense, and the wildfires tend to be not as severe when they're there. Except for the Mammoth Lakes area is probably the main area, and of course Tahoe covers both sides of the Sierra Nevada, so it's
I'm just very familiar. I'm just very familiar with the east side. So
east side, yeah. Well, it's the most beautiful part of California, I think. Yeah, I go there wherever I can. Whenever I used to live in Pasadena, and I would drive up there. I would spend a month in the Sierra Nevada every year. Yeah. Okay. How deep rotted are trees on average? How deep rooted? Yeah. Well, the root zone are. We had measurements down to. Let me say root accessible water can go down about 6 meters or 7 meters in some of these areas into the sap rock, because we drilled down and we had measurements down that deep, and based on our evapotranspiration calculations at the flux towers, that's where the water had to be coming from, and in fact that's what our data were showing. There's a paper with Toby Ogine as the first author that goes into that soils and subsurface water balance a little bit more than some of my papers. Yeah.
Can you use water isotopes to help like track what depth they're getting their water from at different times, or is that kind of too mixed at that point?
No, no, you can. And my colleagues down in Arizona, I used to be at the University of Arizona, have done that for years to show that pre-monsoon and post-monsoon water is coming from different depths in the San Pedro Basin. We don't need it here because we had direct measurements, but and we didn't really budget for doing that. But yeah, it's a great tool.
one item that you talked about that might not have hit home to some people because they're not experienced, it's just that when you see the pile of trees that you've piled up and the need to remove them from that, it's the fact that in the Sierras, when you're up high, there's just not very much water to begin with, and it doesn't decompose like it does here. Like that pile will be there for 50 years and you wouldn't know the difference.
Well, so carbon storage, good point.
Yeah.
Carbon storage is one of the goals of forest restoration. And so if you can leave it there and it doesn't burn, that's great. That's good.
Right.
That's great. We have another paper that's almost ready to submit that where we basically conclude that if you want the Sierra Nevada to be a carbon sink instead of a carbon source in the warming climate, you've got to have a biomass economy that will take the trees out and even the small stuff and sequester it somehow into wood products. Because with a warming climate, the heterotrophic respiration just speeds up and overtakes the primary productivity. Yeah. So yeah,
They know there are some dead tree stumps that are from over 100 years ago,
yeah.
and that are still there. Like they're just dried up and they're just not doing anything. So
No,
that's
we need.
that's good carbon storage, but it's also tinder for the fire. So there's that.
It is.
trade-off.
That's the double-edged sword, as they say. So yeah, we got to keep the carbon in the forest if we can. But heterotrophic respiration and wildfire both, and we've got to remove some of it with controlled burns. Basically controlled burns are putting carbon back into the atmosphere immediately that could come in slowly due to heterotrophic respiration. But we've got to do the controlled burns to control the projected flame length and protect these rural communities and so forth. So yeah, it's, as I say, it's a wicked problem.
Thank you.
Yeah. So we've only got about 30 million acres to manage here.
Doable. Well, thank you so much, Dr. Bales. Any other questions?
Thanks for the lively discussion. It got me awake.
Well, thank you so much. It was a pleasure to have you in this webinar. So we can all thanks Dr. Bales for speaking today. And
Okay. Good luck. Keep up the good work with your.
you as well.
Yeah. Okay. See ya. How about you?